Number 53 talks about sound becoming louder as you get closer to the source. And we're going to answer this question with intensity. Intensity and loudness aren't exactly the same thing, where intensity is an objective measure of the sound and loudness is a subjective, that is, opinionated measure of the sound. The two are proportional to each other. And so if I played two sounds for you, the one that was more intense would be the one that you'd say would be louder. So look what I drew here. I drew a sound source, and maybe right here's that sound source, and it's let's say it's putting out 100 watts. Now that means that every second it's putting out 100 joules of energy. Now that means that there is an amount of energy on each one of these circles. These are compressions, high pressure areas in the air. There's an amount of energy. I'm not saying there's 100 joules on each one, because it doesn't take a second to make a compression. If it did, then that would mean that it would only be on half a hertz, and that's just not the case. So anyhow, there's an amount of energy on this circle. There's the same amount of energy on this circle. There's an amount of energy on this circle, and they're all the same. Now, do you see something? Since this inner circle is so much smaller than the outer one, and when I say circle, I'm really meaning a sphere, and so I'm talking about the surface area of a sphere. We know that each one of those has a surface area of 4 pi r squared. And so if I'm standing here, well, there's a little eardrum's amount of the sphere that I'm intersecting. If I'm in here, my eardrum's the same size, but how much energy is on that eardrum size is going to be much larger. And so all that is to say, I have an intensity here that's going to be rather small, and I have an intensity in here that's going to be a lot bigger. And for you math types, you know that intensity is power divided by area. That is power divided by 4 pi r squared. Well, in this picture, the r is, well, this is my little r, and here is this big R. And so this intensity is going to be a power divided by 4 pi big R squared, whereas this intensity is going to be that same power divided by 4 pi but little r squared. And if I have a little denominator, well then, hey, I'm going to get a big intensity, and you're going to say that's loud. Put a few stars around that number 53 before we leave it. Number 55, they ask if you double your distance from a point sound source, by what factor does the intensity change? So say here's a place where the sound is coming from, a speaker or an instrument or something like that. And so say here's a spot where you're listening to it from at first, and you're at a distance r away. The intensity that you hear right there is going to be whatever the power is divided by 4 pi times that. Let's call it r1 squared. Now if you double that distance, maybe you were back here now, now your r looks like this, big R2, which is twice R1, and so the intensity out here is the same P divided by the same 4 pi, but now divided by 2 R1s squared. How big is this fraction compared to the blue one? It's a fourth as big. A fourth times P over 4 pi R1, aka a fourth as big as intensity at the red spot than the blue spot. Put a few stars around that before we leave it. '47, they have a speaker and they're going to make some changes to it. They're going to change the power, they're going to change the area, and they want to know what happens to the intensity. So to start off, let's say we have a speaker here, and say here's a spot where the sound is spread out over a sphere. like so. And so we're a distance r away from this, and so our intensity that we use to compare with is whatever the power of this is, however many watts you have, divided by 4 pi r squared. Now you go to a place where the area is doubled. And so that's not twice as far away. That's square root of 2 times as far away, because I want a sphere whose area is twice as big. And so that's going to be like 1.4 times as far. So maybe this person is something like right here. This sphere, it's bigger, it's twice as big, because its area is 4 pi r2 squared, and they told me that that had twice the surface area. So where up here I'm saying this has a surface, this denominator has a surface area of A. Now this has a surface area of 2A. Now how much intensity do I have out here at the blue circle? Well, I am going to double the power like they said. So now we've got a bigger source, 2p. So I have 2p in the numerator, and now I have double the area. So I have 2 times 4 pi r squared. Okay, and just to keep this color coded up for us, that r is the black r in the first place. The 2 is coming from them telling me that the blue one is twice as big, so it's twice as much area as I had before. And look at these two fractions. This fraction, p over 4 pi r squared versus 2p over 2 4 pi r squared. What happened to this intensity? Well, those 2's are going to cancel out, and it's going to give you the same intensity as you had before. So since intensity is power divided by area, if I have twice the power but twice the area, those two things are going to offset each other, and it's going to give me the same thing. So on number 48, they say, what area does a sound with intensity of 0.067 watts per square meter pass through if the power of the source is 0.21 watts? Now, anybody can just put the numbers into the equation, but we got to understand what this thing means. So say we had a sound source right here. Let's say the sound is spreading out, and maybe a sound wave is produced. There's a compression, and then it gets bigger, and then it gets bigger. Well, as it keeps getting bigger and bigger, it gets less and less intense because the power stays the same, but the area gets bigger and bigger and bigger. And so maybe at the middle one, the intensity is medium size. Power is the same as it is on the other one, but the area is smaller. And maybe on the very most inside one, the intensity is really big, because the power is still the same size, but the area is teeny tiny. So they're saying one of these intensities is 0.067. Let's make it the medium one, not too big, not too little. So let's say this intensity is equal to 0.067 watts per square meter. And they say, all right, and so the power from the sound source is 0.21. That is, the numerator is 0.21 watts. That's going to be the same on all of those, you see. But the areas are different. If you divide 0.21 by a big number, you're going to get a small number. If you divide 0.21 by a small number, you're going to get a big number. Well, they're saying, how big you got to let that sphere get out to? How much surface area does that thing have to have until it has an intensity of 0.067. All right, so solving this is dead easy. You can take this intensity equation and you can solve it for the area, and you can say it's the power divided by the intensity. So all you got to do is go 0.21 watts by the 0.067 watts per square meter, and that's going to be 3.1 square meters. So you got to let that thing get big enough so that all that energy is spread out over 3.1 square meters. If you do, you'll have the intensity that they gave you. See, anybody can put the numbers into the equation, but now you know why. On example 1410, there are two people listening to a bird. And here's the bird up here in the tree. And you can see they're drawing the bird's sound waves, the compressions spreading out like this. Well, whenever the sound finally intercepts this person's ear, there's an intensity that's the ratio of the power to the area. So now, they tell you that the intensity, that ratio at that spot, is 2.8 times 10 to the minus 6 watts per square meter. They want to know what's the power, that is, how much energy is a bird putting out every second. Well, that's pretty easy. We can just say that the intensity, power divided by area, so that says that power is intensity times area. So I'll just do 2.8 times 10 to the minus 6 watts per square meter times the area. Now, this person is a meter away, and we're going to assume that the sound is just spreading out in spheres, and in fact they say assume that no sound is reflected or absorbed, so you're not losing any of the energy, and you're not part of a reflection where you're actually getting waves from two different sources. So all that is to say, where we use 4 pi r squared, 4 pi times 1 meter squared to give us the area that sound is spread out over. And if you go ahead and run that through, you're going to get 3.52 times 10 to the minus 5 watts, or that many joules per second. Now, in part B of this, there's this other observer, and they want to know what's the intensity heard by the second observer that's much farther away, 4.25 meters away from the bird. Now, this observer, being so far away, is going to be part of a huge sphere, and so it's the same power, but now this area is gigundo, and so that means this intensity is going to be teeny tiny like that. So now you could go about this, like I said, a couple different ways. You could just say, all right, well, that power is 3.52 times 10 to the minus 5, and then divide by that area, 4 pi r squared, 4.25 meters squared. And you can go ahead and get 1.55 times 10 to the minus 7 watts per square meter. And that's a pretty easy way to do it. The other thing you could do is you could say, hey, the same power on this black sphere as is on this red one. And so you could say that since the power on the black is equal to the power on the red, let me get that in red, power on the red, well, then that means that the intensity times the area on the red is equal to the intensity times the area on the black. And so all that is to say, you could say this intensity on the black is the 2.8 times 10 to the minus 6 watts per square meter. And the area of the black is 4 pi 1 meter squared. And that's equal to the red intensity times the area. And that red intensity times the area is going to be the answer we want, times 4 pi times 4.25 meters squared. Now, this is kind of neat because those 4 pi's are going to cancel out. The 1 meter square isn't going to make any difference. And so really you can see that this intensity is at 2.80 times 10 to the minus 6 watts per square meter divided by 4.25 meters squared, like that. That meter square actually is going to cancel out with this meter square. It's just going to give you an intensity. And guess what? It's exactly the same way to do it. You can take your pick. And then on number 49, they want to know how far away should a third person be so that they have an intensity of 7.4 times 10 to the minus 7 watts per square meter. Well, if you think about this, this person that was real close to the bird, they had an intensity of 2.8 times 10 to the minus 6. That's what they gave us. in the problem. And then this person that was much farther away, we calculated they had an intensity of 1.55 times 10 to the minus 7. Well, if you look at the number 49, there's an intensity that's sort of in between there. So I'm hoping that this comes out to somewhere in between those two. Let's see if that's the case. So it says that how far is the person from the bird? Well, we know that intensity is power divided by area. So I'm going to say that the area is the power times the intensity. So now I'll take the power that that bird had, 3.52 times 10 to the minus 5 watts per square meter, and then multiply that by the intensity, 7.40 times 10 to the minus 7 watts per square meter. Now I have to do a little more to this because this is not equal to the distance, it's equal to the area. And so it's equal to 4 pi r squared. So I'm going to need to divide that by 4 pi and then take the square root of both sides. And after I do that, I will get something in between there. 1.946 will make it 1.95 meters. So in between those two observers is where that intensity is going to be. On 50, what's the power of a point source that has an intensity of 3.2 times 10 to the minus 6 watts per square meter at a distance of 48 meters? So we know that intensity is power divided by area. So they want us to calculate that power. So how about we say power is intensity times area? And so we have an intensity right here, and that area is going to be 4 pi times the 48 meters squared, and I'm going to get a power of 0.09265, just two significant figures on that, 0.093 watts. Given the powers and the distances, number 51 wants you to rank the intensities. We know that intensity is power divided by area. So I'm going to do the power divided by 4 pi r squared 4 times. Now I'm actually not going to need my machine on this because they just want me to rank them. So I'll be able to rank them just by saying that the intensity is whatever the power is. In A, it's 10 watts, divided by 4 pi and 1 meter squared. So just in my head, I can say that that's 10 over 4 pi. Yes, it's in watts per square meter. Now, that might not be very friendly, but I'll be able to rank it very easily with that. How about 20 watts for B over 4 pi and 2 meters squared? And so 20 over 4, 5 over 4 pi watts per square meter. Intensity for C is a similar thing. It's going to be 50 watts by 4 pi times 5 meters squared. 50 divided by 25, that's going to be 2 over 4 pi watts per square meter. And then last for D, intensity of D, 100 watts by 4 pi and 5 meters squared. You know this is going to come out bigger because it's the same denominator as the last one, but it's twice as much numerator. And yeah, it's 100 divided by 25. It's 4 over 4 pi watts per square meter. You might be real tempted to divide those 4s, but I'm not going to because all the other ones have 4 pi in the denominator. So I'm supposed to make this in increasing order of intensity. It looks like intensity of C is the smallest. It's only got a 2 in the numerator. And then D, and then B, and the biggest was A. All right, on 97, they talk about a warning system in Hawaii for tsunamis. It says, suppose a siren produces a sound that has an intensity of 0.5 watts per square meter at a distance of 2 meters away from it. Now, when I first read this, I thought, man, they could crank it up a little bit, because usually they say that the threshold of pain is 1 watt per square meter, and this isn't even there. Now, you'd think if you were standing 2 meters from a tsunami siren, you'd have to hold your ears. So I thought, wow, they should really crank it up. But then you watch at the end at what the answer comes out to be, and maybe the joke's on me, and maybe I don't know what I'm talking about. Anyhow, it says treating the siren as a point source of sound and ignoring reflection and absorption, find the intensity of a sound at a distance of 12 meters, 21 meters, and then they say how far away could you possibly hear the sound. Okay, so what I did first is I said, all right, well, if they tell you what the intensity at a certain distance is, then you should be able to calculate the power for the sound. And that's how I'm going to solve part A. So for part A, I'm going to say the power for the sound is the intensity times the area. Okay? And so I'm going to take that intensity of 0.5 watts per square meter, and I'm going to multiply it by the area. Now, don't just go with 2. You need the area of a sphere. 4 pi times 2 meters squared, like this. And you go ahead and do that, and you get a power of 25.13 watts. Okay. Now, that's going to be the power on every one of those circles. So if I wanted to draw the tower, the siren, and I drew a circle, there's 25.13 watts. There, they all have the same amount of power on them. Okay, so now I can take that number and I can use it then to solve for the intensity that's 12 meters away. Because if the intensity is that power divided by that area, now I can take the 25.13 watts, let me get out of your way, and I can divide it by the area. That's going to be 4 pi times 12 meters squared. Now, that in and of itself is going to give you an intensity of 0.0139, just 2 significant figures, watts per square meter. Now, some people are going to look at that and they're going to say, wait a minute, you multiplied by 4 pi and now you're dividing by 4 pi. That was kind of a waste of time. And those people do have a point. So I'm going to do part B a different way. Now, you could do part B exactly the way I did part A if you wanted to. But one thing you could think about is you could say, all right, so maybe in part B, maybe this is where you're 12 meters away, and maybe here's where you're 21 meters away. And what's true about those two, not the intensity, not the distance, not the area, but the power is the same between those two. And so somebody might say, and if you don't like this way, you can do it exactly the way I did part A, just put a 21 in that denominator. But look at this. You might say that the power at 12 meters is the same as the power at 21 meters. It's just that the power at 21 meters is way spread out. So then if the power, if that's going to be the intensity times the area, okay, and that's going to be at 12 meters and at 12 meters. And now here I have an intensity at 21 meters and an area at 21 meters. Now, that intensity at 12 times 4 pi r at 12 squared is equal to the intensity at 21 times 4 pi the radius at 21 squared. Now, here's what they were talking about before. The 4 pi's are going to cancel out. You see that? And so now I could say that the intensity that I had before, that's at 0.0139 watts per square meter, times the radius of 12 meters squared, and that's equal to the intensity, that's the answer we want, times the radius of at 21, which is 21. And so if you go ahead and multiply the left side and then divide by the 21 square, you will get the same thing as if you had just put the 21 in there. 0.0045. Notice how it's a lot less intense than it was at 12. Well, it should be. Now in part C, and I think part C is pretty neat. In part C, they say, well, how far could you possibly hear this siren? Because if you keep going out farther and farther and farther and farther, eventually it gets so soft that you can't hear it. Maybe your dog would be able to hear it, but you wouldn't be able to hear it. What can humans hear? Well, we take it for granted that the threshold of hearing for a human being, we call that I naught a lot of times. And again, that's the threshold of hearing. And we say that that's 1 times 10 to the minus 12 watts per square meter. Now, that's an average. I can't hear that. And some of you can't hear that either. But some of you can, and some of you could actually hear a sound even softer than that, less intense than that. Good for you. But they say, we take this as the average. And so they say, well, how far away could you possibly hear this? Well, we could say that, how far away is the intensity all the way down to this? Okay, so like I have been saying, intensity is power divided by area. And so the answer, the distance is in that area term. So let me make this area is power divided by intensity. And so that's going to be power divided by an intensity of 1 times 10 to the minus 12. And at the same time, that's equal to 4 pi r squared. So I could say that the r squared is the power divided by 4 pi and the 1 times 10 to the minus 12 watts per square meter. That power is the same as that power has been all along, 25.13 watts. So if you go ahead and get the fraction and then take the square root, you're going to get 1.41 times 10 to the 6th meters. And I had to check myself on that. Is that right? Turns out it is right. That is 14 kilometers. And I converted that. That is 876 miles. So I guess it's loud enough. I guess they don't have to make it any louder than that.